Hello everyone, I'm Shi Xuansun from Shanghai Jiao Tong University. I'm very happy to join this event. And next I would like to introduce our recent work on improving the graph computing with cloud technologies. And this is about the fast graph is enabling scalable, efficient, and cost-effective graph processing with serverless computing. And this is a joint work with the National University of Singapore. And the related paper has been published in this year's S+. Firstly, we are going to briefly review the background of graph processing systems. And graph processing has become essential in various areas, such as the social network mining, recommendation systems, and the road network analysis. And to meet the specific demands of these tasks, and the researchers have created targeted framework designed to handle large graphs efficiently in both shared memory and distributed environments. And when deploying these frameworks, users have the option to purchase the physical servers or allocate cloud-based virtual machines through the infrastructure as a service platform. This is called IaaS. And graph processing generally follows an iterative execution flow, which can be visualized through a simple diagram. Firstly, during the pre-processing phase, the original graph is partitioned into multiple subgraphs with a focus on maintaining the load balance and minimizing the communication overhead. And this phase involves creating and distributing the CSR index and other auxiliary structures, incurring significant computational cost. And next, during the actual execution of graph processing, a coordinator assigns the tasks to each subgraphs and primarily specifying which vertices are active in the current round. Next, each subgraph begins its computation by scanning the edges and updating the vertex values according to the user-specified algorithms and the UDF functions. And then, after the computation, the subgraphs must synchronize their updated vertex values to maintain the consistency, and which entails the expensive auto communication. Finally, the coordinator gathers results from these subgraphs and decides whether to initiate computation in the next round. And this interactive process continues until no further vertices updates can be made. However, the IaaS-based graph systems often lack the elastics to manage the fluctuate workloads. Here, we present a real-world workload pattern from a graph processing on a city road network. First, the blue curve represents the normalized queries per minute over the course of a day. And then, similar to the typical IaaS configurations, we establish a fixed VM cluster setting. And this is shown by the red line, and indicating consistent resource processing capability. And this figure highlights two main issues for IaaS-based systems. The first, the query spikes can arrive randomly, resulting in a surge tail latency due to the insufficient computing resources. And second, during the periods of low workload, a significant amount of computing resources would remain underutilized. So we are shifting towards serverless computing. And this emerging cloud computing paradigm provides three main advantages. The first one is that it has high scalability, often implementing the unbounded scaling policy as the default auto-scaling mechanism. And this means that when a query arrives and no idle container is available, then the platform automatically initiates a new one. Secondly, is about the billing skills, the billing methods. It offers a pay-per-use, a very fine-grained billing system that charges based on the resource usage rather than the resource allocation. And thirdly, it amplifies the management for users. With cloud platform managing the underlying infrastructures, users only need to upload their source code and data. Then uh, the emerging serverless paradigm inspires us to whether we can integrate the graph processing with the serverless to benefit both of them. To this end, we conduct profiling studies by executing Gemini, a SOTA system within the simulated fast functions. And this setting is referred to SR as the second rules. And additionally, we also include an extra setting named SD. And this one enables the direct communication between functions. And the table below shows the performance breakdown of the three configurations in a representative graph workload executing the PageRank algorithm. And we observe that first, the direct mitigation to serverless can degrade performance, even with low resource initialization latency and direct communication between functions. The second is about the graph I/O and pre-processing. And these operations often occur during the cold start phase, and it can dominate the performance. Next, we evaluate the performance from the cloud provider side. We conducted a profiling study focusing on the memory footprint throughout the day using the previously introduced real-world graph processing workload. For the figure below, the green line illustrates the allocated memory of serverless containers, whereas the orange line reflects the actual memory utilized during the computation. Now, let's see that at 10 a.m., there is only one container in operation when a sudden query spike occurs. In response, the system will quickly scale up to accommodate the increased demand for graph processing tasks following the unbounded scaling policy outlined earlier. However, with the newly launched containers occupied by the lengthy graph processing tasks, the system had to initiate more containers to handle the remaining queries effectively. This is called the excessive scaling, which arrives when newly deployed containers cannot quickly address incoming queries. And this will force the system to initialize additional containers to handle the queries. And finally, the underutilized containers are recycled after a keep-lived period. Given that those containers remain inactive after the query spikes, the memory resources are left unused and then wasted. So our conclusion is that the unbounded scaling method will lead to the allocation of excessive resources, often resulting in the wastage during the keep alive period. This would waste a lot of money for the cloud providers. So, inspired by our investigation, we introduced FastGraph, a co-designed scheme that combines the graph processing and serverless architectures. And the following diagram illustrates the executing flow of a FastGraph. The first step is for the users. They can start by uploading the functions, the graph dataset, and the resource configurations. Then, when a user sends a request, the scaling controller will retrieve containers from the resource pool and loads the necessary graph dataset if required. And the graph dataset is generally in the cloud storage. And subsequently, the containers will begin executing iterative graph processing tasks controlled by a coordinator. And in the subsequent sections, we will dive into the details of our designs within the FastGraph, including three key techniques. The first one is resource fusion, and the bounded scaling, and some graph optimizations. And because graph datasets are typically large, as we introduced before, and the resources allocated to serverless containers are generally very small, so we need to coordinate the multiple containers to handle a single graph query. Our key insight is that we can employ unified and fine-grained containers for graph processing while retaining the scheduling flexibility. To achieve this, we introduced the container set abstraction, which include fine-grained containers and each responsible for processing a subgraph. As shown in the figure, these containers can be distributed across multiple servers and collected with large containers or VMs from other users. And this flexibility in scaling enables us to leverage idle resources scattered across multiple servers, and then it can improve the cluster resource utilization. However, the scattered containers could introduce extra communication overhead, which could degrade performance. And to address this issue, we aim to recreate the locality by employing the resource fusion. And this involves the simulating an environment similar to having a single large server instead of multiple small containers. Specifically, we have two techniques. The first one is called the local resource fusion. And when containers are physically located in the same server, we can optimize the load balancing by sharing their CPU resources. And furthermore, we can utilize the shared memory segment to establish fast data synchronization channels. The second technique is called the remote resource fusion. For the containers located on different servers, we introduce message consolidation and the async transition to further optimize the communication performance. And next is about the scaling strategies. And despite the introduction of container set, uh, the, the default scaling policy will still result in memory waste, as we outlined earlier. Moreover, the significant memory demands associated with the graph processing worsen the problem. So we propose our new bounded scaling policy. The key idea is that rather than immediately allocating the new resource, we wait for the current occupied resources to become available. And shown in the figure, upon the arrival of a query, it initially selects the shortest queue to join. Additionally, we estimate the cumulativity for each query to assist in the decision making. If the estimated queuing latency for current query exceeds the cold start latency, then the system falls back to the cold starting to new containers. By adopting the bounded scaling policy, we effectively reduce the memory footprint by mitigating the excessive container scaling. Simultaneously, we enhance the prolonged close start because we can place some queries on the warm containers. Next is about some graph optimizations. We have also revisited many design choices from previous graph systems. We have introduced the single mode. It's called main vertices start the message passing to reduce the overall memory usage, and introduce the fast graph loading to reduce pre-processing overhead. And due to the time constraint, we omit the details here, and you can refer our paper for the details about the graph optimization. Next, I will introduce our experimental results. We have evaluated fast graph across a range of graphs and graph applications, and utilizing both a small cluster for one-shot query analysis and a large cluster for a case study. And the specific resource configurations are shown in this table. And additionally, we incorporated several state-of-the-art graph systems baselines for comparison. For example, the Gemini and Graph 8. Our first result is about the single query. And our experiments show that the fast graph improves the end-to-end performance by up to 8.3 times and reduce memory usage by around 50% compared to SOTA systems. Simultaneously, the fast graph demonstrates the low memory scaling overhead and resource increase. And secondly, it achieves the balance between the cost and the performance. We have also conducted a case study using the query pattern we just outlined before. We compare a fast graph Gemini and a naive scaling version of Gemini. The naive scaling means that we will modify the number of Gemini instances every 10 minutes based on the prior knowledge of the query pattern. And according to the table, introducing fast graph can lead to up to 85% of the daily monetary cost savings. And the bottom left figure illustrates the tail latency during the rush hours. As shown in the figure, the fast graph represented by the green curves almost entirely eliminate the tail latency sorted by the workload fluctuation. And this is attributed to the fast graph's automatic scaling. And when applying the bounded scaling policies, the memory cost will be reduced significantly. To summarize, the IaaS-based systems struggle with the fluctuating workloads. Hence, we present the fast graph, a scalable and cost-effectiveness billing edge graph processing engine. And by introducing the resource fusion, bounded scaling, and the graph optimizations, we aim to narrow the gap between the serverless and the data-intensive analytics. And our experiments have demonstrated the fast graph delivers substantial performance improvements. We have open source all the source code at GitHub, and if you are interested in it, you can download the source code. And thanks for your listening.